Great. So our next speaker is Aram Dermenjian, who will talk to us about Bruhat preclosure.
Hi everyone. Uh, Thanks for letting me talk here today. I hope everyone's having a fun day wherever you are on the planet. So like as Foster said, I'll be talking about Bruhat preclosure. So we'll start off with the super basics on Coxeter groups. So I think most people here know what these are, but just to set some notation and to give like a quick overview for people who don't. Coxeter groups, we have a finite generating set. S, which generates the group W. W will be our Coxeter group. And between any two elements in our generating set, we have some order which sends them to the identity. So Sij to the power Mij gives us the identity. And every element is a reflection. So whenever we do the operation twice, we get back to the identity as well. Now, in order to not write the whole presentation for Coxeter groups, a lot of times what we'll use is what's known as a Coxeter diagram, where we'll take our generating set S and we'll let these be our vertices. And between any two generators, which also we'll call simple reflections at times, we'll draw an edge whenever this Mij, this power, is greater than 3. If it's equal to 3, then we just draw an edge without a label. And if they commute, so the order is 2, then we won't draw an edge between them. To show why Coxeter diagrams are a little bit nicer, here we'll take what's known as the type B3 Coxeter group with this presentation. We have 3 element generators. Everything is a reflection, so S1, S squared, S2, S squared, and S3, S squared all go to the identity. Between S1 and S2, we have a power of 4. So what we'll do is we draw an edge with a 4. S2, S3 has power 3, so we draw an edge without a label, and S1 and S3 commute, and so there's no edge between S1 and S3. So people who are used to Coxeter groups will know that there's a lot of different types. So some different Coxeter groups are, for example, the symmetric group, where the simple reflections or the generators are nothing more than the simple transpositions, the adjacent transpositions. Yeah, and so we have the symmetric group. We also have the dihedral group. And we also have basically any kind of Coxeter group we want. So we can have infinite groups. We can even have edges labeled with infinity. And when we have infinity, basically we're saying these two relations don't have, these two elements don't have a relation between them. So this allows us to generate basically given some graph with some labeling of positive numbers or infinity, we can generate a group from there. Now, what we're going to do with this is we're going to look at words using the generating set. So whenever we have some element, we can write it as a word over the generating set, and we can define the length of an element to be the minimal length that we need this word to be. And that word will call a reduced expression. So for example, if I have just 2 generators, S and T, which here, if you remember, this means that the order between S and T is order 3. So ST to the cubed gives us the identity. And so if I take some element S times T times S times T, and I want to know the length, it's going to turn out that this is 2. And why is that? Well, I can look at ST, yeah. And since I have this relation ST cubed gives us the identity, I can rewrite this as STS is equal to TST. So I convert STST to TSTT, and now T squared is just the identity. So I can remove that, and I'm left with TS. And so this is why we can kind of reduce and get a length 2 element. So TS would be a reduced expression of STST. Now, most of the time we'll be looking at just reduced expressions. And so based off this, what we'll define is a right-weak order. So the right-weak order is just a prefix order on elements, okay? And in this case, you can kind of see this. The reason why we're calling this right is because we're doing multiplication on the right in order to go up in our partial order. Yep. So this is one of the orders we'll be playing with. And as you can see, if for the graph we had before, this is going to give us this nice hexagon that I'm sure most people in this audience have already seen quite a few times. So from here, we're going to look at another set, something that is related to the weak order. And these are called the inversion sets. So an inversion set is just what we start with is we start with the conjugates of all of our simple reflections. And that's going to give us a set of all reflections. Okay. So when this might be an infinite set, so it's not always finite, but that'll give us a set. And here, instead of thinking about multiplying on the right, we're going to think of multiplying on the left for the inversion sets. And whenever I multiply on the left by a reflection and the length goes down, then I'm going to put that element, that reflection, into the inversion set of the element. So n of w being the inversion set is basically the set of reflections in which my length goes down when I multiply on the left by that reflection. So going back to the example we did previously, if I look at TS, so remember this had length 2. The inversion set for this is going to be 2 elements, T and TST. And we can see that by just doing the multiplication. So if I multiply on the left by T, T times T, again, that's just going to give me the identity, so that disappears, and I'm left with just S. So since I'm left with just S, that's the length 1, so the length has gone down. Now, similarly, TST, if I multiply this on the left of TS, then I'm going to have TS, so the inner T's cancel. And once those inner T's cancel, the two S's join up, and those will cancel as well. So I'm just left with T as well. So again, the length goes down to just one length. And there's a nice, easy way to actually generate the inversion sets given some reduced expression. And you just go from left to right doing conjugates. So I start off with S1, and then I conjugate the second one by everything before. So S2 is conjugated by S1. Then I take S3 and I conjugate by S1, S2, all the way up to Sn. And I get S1 up to Sn minus 1 in order to get the generating set, the inversion set. And so here, it's not too hard to see how we got the inversion set for TS. You just start with T, then you do TST. For something a little bit more complicated, if I take these, the type A3, so RST, now I have a third generator. If I look at RSTSR, again, I can just go one at a time and do conjugation. So I start with R, then RSR, then RSTSR, then RSTSTSR. And that will actually reduce down to T. And then finally, we can do the last one where I just take the conjugate of RST or R by RSTS. And that'll reduce down to TST. So those are the reduced expressions. Now, the nice thing about this is that the weak order is associated to inversion sets. So we can actually just view the weak order as containment in inversion sets. Okay. And so here on the left, we have the weak order, and here on the right, we have the same inversion sets just given. Now, the nice thing about these things, most people know that by a result by Björner in 1984, the weak order is known to be a meet semi-lattice. And if W is finite, then it's going to be a lattice. Now, what do those mean? So a meet, it just means that any two elements has a greatest lower bound, and a join is a least upper bound. And a meet semi-lattice, meaning every two elements has a meet. Join semi-lattice, every two elements have a join. And a lattice that every two elements have a meet and a join. And so in particular, to see these as examples, this the one we've been working with this whole time is a lattice. Every two elements have a meet and a join. If we look at a slightly larger one, the one with 3 elements, again, this every two elements are going to have a meet and a join. But for something that's infinite, so for example, if I take the infinite dihedral group, every two elements will have a meet, but not necessarily a join. So here, if I take something on the left and something on the right, they're not going to have something above both of these. Yeah. Now, we're going to change things slightly, and we're going to look at a different way of looking at these elements. So everything from before, we've been multiplying by just simple reflections. So the Bruhat graph is a similar thing, except instead of multiplying by simple reflections, we're going to multiply by all reflections. So here, in this case, the vertices are, again, all of our elements. And we draw an edge from some element to another. When we multiply on the right by some reflection, the length goes up. And here, I really do want some directed graph, right? So if I go from S to TS, I'm multiplying on the right by STS to go from S to TS. So this is what we're doing. And we're going to want the directedness because we're going to actually mess around with this graph later on. And the way we're going to mess around with them is by something known as A paths. So if I take my reflections, all of my reflections, I can take some subset of them. And an A path is just going to be a path in this Bruhat graph that just follows only the edges labeled by the reflections in A. Okay? So for example, if I have my A be just the set S and STS, where here my set of reflections is these three elements, well, I'm going to only look at, in this case, the red and the black edges. So the ones that are labeled S and STS, and I'm left with this subgraph. Yeah. And what you'll notice is something a little bit nice happens. If I look at the identity and look at where the identity goes, like what paths I can take from the identity, I'm going to hit only two reflections. And the two reflections I hit are precisely the two that I started with, S and STS. I can't get to T. Now, looking at a different example, so if I take A to just be STS, so I only keep the middle three arrows, a very similar thing happens. I'm only left with STS. If I, and this is basically the idea of the Bruhat preclosure. So the Bruhat preclosure is basically saying, look at some subset of your reflections, and if there's an A path from the identity to a reflection, I'm going to take that reflection and I'm going to keep it. I'm going to add it to the closure. Now, in the first two examples we saw, these were precisely the same sets. Yeah, but it's not too hard to see that if I were to take my elements to be S and T, my generators. Now, remember from the weak order, that just means I'm going to go to every single element. So I should have every reflection. So we can add new elements. And so the Bruhat preclosure doesn't always just give us the same set we started with. We are potentially adding new reflections in here. But the kind of nice thing here is that if you're a little bit quick, you would have noticed that the first and the last one are inversion sets. And in particular, the bottom one is a very nice inversion set. It's the inversion set of the join of S and T. So it's the join of my two simple reflections. Yeah. And so in some sense, this inversion set, taking the closure of S, the Bruhat preclosure of S and the union with T is going to give us every single element. And so this is basically an idea from Matthew Dyer. He had a conjecture from 2011, which basically stated two things. One is that that the Bruhat preclosure is a closure operator. And the second is that you can actually take the join, find the join using this operator. So in particular, he conjectured that if you take the join of two elements and look at the inversion set, this should be the same thing as just taking the union of the inversion sets and taking the preclosure of this. Now, based off the words I've been using, you should probably have guessed that there's going to be a slight twist here in that this first thing is false. It's not actually a closure. So there's a counterexample. And here's the counterexample. This is in type H3. And so if I were to start off with these four reflections, so these are the four reflections in black, bolded with a thick border. So here, 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 and here. And I look at all the different reflections all the different elements I can get to. These are all the black solid lines. So that gives me all of those reflections. I will eventually get to this reflection here in blue, RSRSR. That's going to give me a new element. So now I'm going to take the Bruhat preclosure of this. That's going to add all the dashed blue lines. But if I add all the dashed blue lines, I'm going to get a new reflection. And that's going to be the reflection RST, RSR, T, RSR. As long as I wrote that right. And so here we can kind of see this breaks the closure property, where if I take the closure, two times, I should get back to the closure. I shouldn't be able to keep getting new elements as I keep doing closure operators. So this turns out to just be a preclosure. And so the question becomes, can we do something about this? Can we fix this? And in order to fix this, we're going to actually take this a little bit further, and we're going to look at what's called reflection orders. So a reflection order is basically taking our set of reflections, and between any two reflections, I want to look at the kind of what's it called? I'm going to create a total order such that the alternating reflections are always going to be alternating. So like either I'm going to have R, RSR, RSRSR, dot, 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 all the way to SRSS, or the opposite of that. So to see an example, if I look at RST, so this is like R3 one, we have two different reflection orders here. So the fact that this exists is pretty cool, and this works for every single Coxeter group, even the infinite ones. And so as an example, looking at any particular pair, if I look at SNT, then I'm going to have three elements being generated by this. And you can see that STS is going to be between TNS for both cases. This is the same thing if I look at RNS. RSR is in between RNS. Between R and STS, again, RSTSR is between the two. And again, RSR and T, RSTSR is between the two. Yeah. And so what we're going to do is we're going to expand the definition of inversion sets to what's called an initial section. So an initial section is basically taking these reflection orders and just taking some initial part of one of these reflection orders. It doesn't matter which one. And in finite cases, these are nothing more than the inversion sets. So RT here, if I look at these first two elements in the first reflection order, that's just going to give me the inversion set of RT. If I look at the first three elements in the bottom reflection order, then I get the inversion set of RST, etc. So here's two more examples. The third one is the first four elements of the first reflection order. I can take nothing, so that just gives me the inversion set of the identity, or I can take everything, and that's going to give me the inversion set of the long element in the case of a finite Coxeter group. Now, it's not always the case that we have things finite, right? So for example, in the infinite dihedral, an initial section could be all reflections that begin with the letter S, right? So this is an infinite set, which means there's not going to be any word associated to it. So we cannot have anything, an inversion set, which is represented by, or which gives us a representation for this initial section. And so what we can do is we can now look at initial sections instead of inversion sets. And in this case, if we look at the dihedral group, something very similar happens. If I look at the inversion set of S and STS, then you'll notice how we have a very similar thing where I'm only getting to the ones that I started with. And similarly, if I look at an initial section, I'm only going to get the ones that I originally started with. I'm always going to stay on the left-hand side of this graph here. No matter how far up I go, I'll never be able to get to any of these reflections here, starting from the identity for these 8 paths. And that's because these Bruhat preclosures work very nicely on these initial sections. So whenever we take the Bruhat preclosure of an initial section, we get back to that initial section. We don't ever add anything new. And this is precisely the things that we had seen from before. This works for this infinite one that we just saw. This works for the finite cases from before. This works for basically everything, yeah? And so what are we going to do with these initial sections? We're going to take these and we're going to use this idea in order to kind of expand on this. So we have this fixes some of it, right? So we don't necessarily have a preclosure. We don't have a closure for every single set, but we have a closure when we're only looking at initial sections. So in some sense, this idea is almost correct. So we want to fix it a tiny bit more. And the way we're going to fix it a tiny bit more is by looking at what's known as finite type preclosure. So a preclosure is a finite type. Whenever basically I take the closure, what I can do is the closure of some element is going to be the union of the closure of all of its finite subsets. Okay? And so that's just what a finite type preclosure is. And we can take the preclosure I times. So by denoting a little I here on top, it basically means I'm doing this I number of times. And I can denote the infinite preclosure as just the union of all these closures, right? And so it turns out when we do this infinite preclosure, then this turns out to just be a closure. So doing this operator an infinite number of times, we get a closure. And the nice thing is that the Bruhat preclosure is actually of finite type. So in other words, a corollary of this is that doing this Bruhat preclosure an infinite number of times will give us a closure. And so this gives us a little bit of hope in order to be able to solve this second question, right? So the first question was, well, is this closure? Well, no, it's not a closure, right? But if we look at the infinite Bruhat preclosure, so doing this preclosure an infinite number of times, well, now it is a closure. So can we use that in order to solve this, to solve the conjecture? And it turns out yes. So we do actually have, doing this an infinite number of times, we will get the this inversion set. Now, a nice corollary of that is that for finite Coxeter groups, we don't have to do this an infinite number of times, right? Because we have a finite number of reflections. And so we only have to do a maximal that number of operators, right? Because each time we can only add, we're going to be adding one each time at most. And so we're limited in some sense as to the number of times we can do this operation. And so in some sense, this is a nice result. We're not 100% of the way there, but this gives us an inclination that this conjecture is probably true. And so there's been a lot of work in recent years in trying to figure out, well, how much of this is true, right? How much can we get rid of this infinity? So in recent years, like I said, there's been a lot of progress. Biaglioli and Proni last year showed that, and myself, we've showed that in the dihedral group case, this is known. We can get rid of the infinity and it still works. This works in the symmetric group as well. So Baglioni and Proni showed this directly, and I also showed this, but in a slightly different way. So the way I showed this myself is by showing that in type A, so in the symmetric group, the Bruhat preclosure is actually just a closure. So in this case, we do get a nice closure for the symmetric group. And so then the question becomes, well, okay, in type A it's nice, and the dihedral type is nice. What about the other types? And this is where there's still a lot of open problems. So recently, Biaglio and Proni have also proved type Bn. I think it's still not on archive as far as I'm aware, but it should hopefully be on archive soon. Type D has been checked only for up to n less than or equal to 5. F and H have been checked by computer. And then type E is also still open, but due to the rank being so high, computer checks are going to be a little bit more difficult for this. And in infinite types, basically everything is still open, and we don't really know much on this end. So even in the finite case, this is a fairly convoluted and difficult problem, but it seems like the conjecture is probably true, and we'll be trying to see what we can do. So yeah, so I'll end it here. This is the type H3 lattice, if people are curious. But yeah, thank you.
Great, let's thank Aram. And are there any questions for the speaker?
Yeah, quick one. What about G2?
G2 is dihedral, right?
Ah, right. Okay, yeah. Thanks. Yeah.
So here's G2. Yeah, so G2 is a vial group which be associated to I26, right? And so this would be handled in that case. That's also why you don't see C, because C in Coxeter group world is just the same as type B.
Okay, could I ask another one then? Also, thanks for the nice talk, Aram.
Yeah.
Why was Dyer looking at this operator, or like, does it have something to do with Kaplan-Lustig polynomial computations at all?
Partially. So he was looking at it for a couple different reasons. Let me get a nicer graph. So there's two different reasons. One, is he's trying to do a lot of Kaplan-Lustig theory, in particular through biclosed sets and stuff. And so what he was trying to do is, so between biclosed sets and inversion sets, you have these initial sections. Yeah. And so he also has a conjecture that initial sections and biclosed sets are the same. As far as I'm aware, that's not been proven yet, and or we don't know if it's true or not. But basically, in some sense, this is in between the two. And so I think his hope in this case was to try to extend the weak order into the infinite case. So, for example, if we look at the biclosed sets, then he has a conjecture that the biclosed sets of infinite Coxeter groups should give you a lattice. Yeah. So in type A, in the finite types, this is obviously true. Recently, it's been shown that in the affine cases, the biclosed sets do give you a lattice. And so the question then becomes, well, is it true for the other one? So this is so these initial sections are kind of like the intermediate thing. And so his hope was, well, it's a little bit easier to work with these initial sections. Maybe we can just use these in order to get to this other idea, as far as I'm aware. But
Well, thanks.
yeah.
Okay, if there are no more questions, let's thank Aram again.